Welcome to Unit 1, Lesson 4, Feel the Energy Move. In this lesson, we're going to look at how to draw particle models and show how particles are moving and interacting at a level at which we cannot actually see. So with your group, you should have already defined all four of these terms, one for each individual, and shared them out. And you should have also then, as a group, come up with similarities between all of them. Okay. Now, and that comprises our rule number 1 here, where all matter is made of particles. It's technically all matter is made of atoms, and atoms make up molecules, compounds, as well as ions. So now we're going to look at Rule 2, which states we draw particles using dots and shade them differently or use different colors if they are different types of particles. A key is required to tell the difference. So for all of these, you will always include a key. Okay, so we're going to go through an example together, and then you will pause the video and work out the other 3, and then you will play the video and see the answers afterwards. Okay, so for our example, we have a mixture of 2 particles. So I'm going to assume that means 2 types of particles. So I'm going to have a purple one. I'm going to call that particle 1. And then I am going to change the color. And I'm going to call this particle 2. Now I'm going to draw enough to create a mixture, but I don't have to encompass the entire thing, because that would be very labor intensive. I want to do enough to effectively communicate the point. So there's one particle. And here is a second particle. So I have a mixture, they're kind of mixed up, of 2 different particles. And that would accurately represent what the example mixture of 2 particles means. Now please pause the video, take 3 minutes to draw each one of these scenarios, so 1 minute each. Okay, so here is the answer that I would find the most acceptable for each one of these scenarios. In scenario 1, it says only 1 particle. So I drew only 1 particle and labeled it this as particle 1. Now I might call this a specific type of element or whatever, or like a water particle, but I have 1 here. Okay, I could, let's see, do I have a pointer? No, I don't. I could have drawn multiples of only 1 particle, and I would have accepted that because that could be interpreted that way. So if you have all the same color or same type of particle labeled, and you have multiple in this scenario 1 box, that would be acceptable. In scenario 2, I have 3 different colors, purple, green, and pink. One that has a much lower concentration than the other 2. And so if I check, that means concentration, I should have fewer in this box that I have here. Okay? And so since pink has fewer than the other ones, that tells me that then I have 1 of these at a lower concentration and the other 2 are higher. Scenario 3 is similar in that I have 3 different particles, but these all have different concentrations. So I drew 2 with only a couple for the pink. The green I drew a little bit more. And then the purple I drew a lot more, so that way I have high, medium, and low concentrations of each one. Okay. You could also, if you are pen challenged or you just don't like having a whole bunch of colors, you could get 3 different colors by shading the boxes in differently, right? And so you could get 3 different colors by leaving one empty, shading one in all the way, and then putting an X in the third one, and that is acceptable. Okay, so we're going to look at Rule 3, which addresses how we draw solids, liquids, and gases differently from each other. And we draw them differently because they each have different amounts of space between the particles. Okay, so solids are generally are really close. And tend to have a repeating pattern. Liquids, on the other hand, have some space between them. This allows them to flow past each other. They do not have a pattern. Okay, now gases have lots of space between. They move fast, and they have no pattern. So we're going to draw each one of these. So solids are really close together. So I draw them touching. Now really close together doesn't mean that they are not moving. They can be moving, but they don't move around. They vibrate in place. It's kind of like when you sit in a chair, you're sitting still or in one place, but you don't sit completely still. You fidget, you shift, you adjust, you cross your legs differently, you turn around in your seat and then turn back. Solids are like that. They stay in one placement, but they move around a little bit in that place, vibrate. Okay, liquids. I'm going to draw a line to indicate that this is now representing a liquid. So pretend maybe this is ice as a solid and then it melts and it's a liquid. They're closer together, but they do not have a repeating pattern. And I'm just drawing this so it's a little obvious. You're going to over-exaggerate some things when you do particle modeling, which is what this is. Okay, so these are close together. We aren't going to draw more or draw any more pattern. It does not have a pattern. Liquids flow past each other and fill their container at the bottom, so they take the shape of their container. Gases, on the other hand, have lots of space between them. Okay, lots of space between them, and we're going to get into how they move, but they move randomly, they don't interact, there is no pattern. Okay, so our next example. Okay, so rule number 4 says that we use arrows to indicate direction, so which way the particles are moving, and the strength of movement or magnitude of a particle. I want to let you know that in general, when we say direction, we're going to imply that this is a random direction. That particles are going to move randomly. It states it explicitly in the example, but it doesn't in each of the scenarios. You're going to assume that movement is random, that they move in random directions, that they aren't interacting as much, unless we tell you, hey, it's wind, which direction is it going? Okay, but that probably won't happen. And the strength of movement, so magnitude of the particle. This strength of movement is related to the temperature of the substance. Okay, because temperature is a measure of the average kinetic energy, or how fast the particle is moving. Okay, or the particles in the substance are moving. Those arrows that we're going to draw on our particles to indicate how they are moving are called vectors. So if I have a large arrow, it indicates it's moving faster. If I have a small arrow, so a big arrow is faster, whereas a small arrow is slower. Faster means a higher temperature. Slower means a lower temperature relative to whatever we're talking about. Okay? So in our example, we have particles moving at the same speed in random directions. It doesn't tell me that I have two different types of particles, so I'm just going to assume that I can say that I only have one type. I'm going to call it particle 1 or particle type 1. I could call it air molecules or whatever. So I'm going to draw some of these so I have enough to represent that this is doing something. Okay. And I'm going to draw arrows pointing in random directions, but they're at the same speed, so they should be about the same length. Okay, I'm not going to take a ruler and check and see if they are exactly the same length. You do not need to utilize a ruler to make sure that it is exactly the same length. You just need to make sure it looks roughly the same length. Okay, so pause the video at this point and take 3 minutes, 1 minute for each scenario, and sketch the models that are there. Okay, so here is the answers for each one of these scenarios. Okay, notice that the arrows are in scenarios 1 and 2 are about the same length because they're moving about the same speeds. Okay, scenario 2 is actually similar to one that we drew before, except this time we added movement arrows. Okay, and they all are about the same length. In scenario 3, they're all moving at different speeds, so the arrows should all be of different lengths. Now, all of these should be pointing in random directions. They should not all be pointing the same way. A couple might be going in similar directions, but they should not all be going in one direction. Okay, here is rule 5, and this is where we introduce the idea of energy transfer, and we can show energy transfer by drawing arrows larger than moving arrows from one region to another or one particle to another. And we're going to look at how that looks or how we could do that. So for the different diagrams below, we're going to create these particle models based on their description. So we have a cold solid. We can say maybe that's like ice, but I'm going to write solid. And then we have warmer air molecules. Okay, so I'm going to draw a little bit of a solid. Why did I shade it in? I don't know. But going fast. Woo. Okay, so I have my solid and I have my air. Now remember, solids move they move very little compared to the air around them, whereas air tends to move much more, or gases move faster than solids. Also, it says that the air is much warmer than the solid. Okay? So our next thing is to add an energy arrow. And we're going to represent energy with an arrow. And so energy flows from where it is warmer to where it is colder. Energy never flows from colder to warmer because cold is the absence of heat energy. If you don't have it, it can't move from there. Okay, so since the air is warmer, energy is going to flow from the air to the solid, and we would label this energy. So complete the other two scenarios. And here is the answer for these. Notice